Sounds good. All right, so we can get it started. So hi everyone. So our GNSS-IR working group is hosting another webinar today. So thanks for joining us today. So we are glad to have Professor Lin Liu from the Chinese University of Hong Kong with us today. Thanks for giving the talk today to us. So just a quick introduction to him. So Lin got his PhD degree from the University of Colorado in Boulder in 2011, and then he moved to Stanford and did a postdoc there before joining to Chinese University of Hong Kong in 2014. And he received the 2021 AGU Air Carrier Award for his pioneering work on the cryosphere. And in fact, today's talk is somehow related to the cryosphere on investigating frozen ground dynamics using GNSS-IR. So I assume that the talk will last around 45 minutes, and then we will have around 15 minutes for question and answer. So please feel free to post your question in the Q&A box and during the talk. And I just shared a while ago, if you're interested to stay updated with news and information, feel free to subscribe to the working group mailing list and also the YouTube channel that the recording will be shared after this talk there. All right, so let's get started, Lin. So it's over to you. Yeah, we are so excited to hear your talk.
Thank you, McCann, for your kind introduction, and you and Dongju for coordinating the webinar series. Let me see if I can share my screen. Okay. All right.
Yeah, you can see it. Perfect.
It's my great pleasure to have this opportunity to talk about how to use GNSS Interferometric Reflectometry, or GNSS-IR in short, for the study of permafrost. It's actually nice really well with what McCann mentioned earlier on, this International Association of Geodesy has a working group on the use of geodetic methods for climate change. Since many of you in the audience are reflectometry experts, but may have not think too much about permafrost problem, so I will take my time today to mainly summarize the scientific insights that we have gained from unique GNSS-IR observations. I will explain how unique it is and how useful this particular method can be in helping us to understand permafrost problems. So I may not get much into the technical detail during my talk, but I'm happy to answer any questions later on. And feel free to enter your questions in chat box or later during the Q&A session. Okay, so when we talk about permafrost, I need to define what we mean by that. Scientific definition of permafrost is referring to ground that remains below or at degree C year-round for at least 2 years. So in that words, permafrost is fundamentally a subsurface thermal phenomena. To help us to understand that, here's a diagram showing typical temperature profile. Horizontal axis showing the temperature, so 0 degrees is right here, marked by the vertical dash line, and y-axis was it's the depth. You see here, red means summer maximum temperature within the ground, and blue means the winter minimum temperature. Within permafrost layer, its temperatures remain frozen. Its temperatures are below or at 0 degrees year-round, so that make a permafrost even in the middle of summer. Okay, but the surface layer, which we call active layer, is a profile showing active layer on top of permafrost. Its temperature can rise above 0 in summer, so it thaws in the summer and freezes in the winter. So keep that in mind, because that's kind of that as a theme for my talk today. We're talking about frozen ground, but actually we're talking about different layers, active layer and permafrost. So since permafrost is important climate system and under the UN Framework Convention on Climate, it's actually classified as essential climate variable, or ECV in short. Then scientifically, when we talk about permafrost change in a warming climate, we need long-term monitoring. Over many decades, the following a few variables, in particular ground temperature, because that's what defines permafrost, and thickness of active layer has been long-termly measured, usually from the fields on the annual base. Recently, for mountain permafrost, there's a new variable called rock glacier velocities being introduced. That's back in 2021, just a few years ago. The last quantity, which is what we're going to focus on in today's talk, is surface subsidence. It's not yet as a well-recognized essential climate variable product for permafrost. But the community has been working very hard, and GNSS-IR has been making contribution to promote the use, the application of geodetic methods to study subsidence in permafrost regions for it to becoming hopefully the next product for representing permafrost essential climate variable. Also shown on this profile, in certain part of permafrost near right beneath active layer, in certain part of the world, permafrost can contain large amount of ground ice. In this case, it's an ice wedge shape. Let me come back to this later on. All right, so where's permafrost? And turns out it is the largest cryospheric system among all the others, among glaciers, among snow cover, among sea ice, for instance. This map shows permafrost extent in northern hemisphere. Different shades of purple represent the extent. The dark purple means in any places over those continuous permafrost region, 90% of area is underlain by permafrost. So, and then we've decreased to discontinuous and sporadic and so on and so forth. Just means the coverage becomes smaller and smaller. So if you look at what's happening in the northern hemisphere from this polar stereo projections, the North Pole's here and Alaska's here, 80% of Alaska, half of Canada, about half of Siberia, the surrounding coastline of Greenland, Scandinavia, of course, talk about Europe, Alps, the high mountains. And the closest permafrost to me, where in Hong Kong, is actually those high mountain areas in Asia, particularly Tibetan Plateau and the Himalayas. So collectively, about 24% of northern hemisphere land is underlain by permafrost. We'll talk about area of 18 million square kilometers. So that's a lot of area to cover. When you think about GPS and GNSS in general, so think about large area for us to cover. Now, we'll talk about permafrost temperature, and here is showing you a review paper a few years ago, synthesized the borehole temperature measurements. Each dot showing here is a temperature borehole that runs for several decades. No matter whether we're talking about Canadian Arctic or Alaskan North Slope or Tibetan Plateau or European Alps, you see here, not just one, not just four, nearly all of the boreholes around the northern hemisphere permafrost region have shown very consistent and widespread increasing of ground temperature. The colder the permafrost region is, actually the larger the rates is. In the relatively warmer areas, because a lot of the heat is used for phase change, for ice to melt. So the warming rates was relatively gentle compared to older places. Here's another more recent synthesis paper, still talking about permafrost temperature change, but in the map view, each circle represents the rates of permafrost temperature change from 2000 to 2019 in over 20 years. The larger the circle is, means the faster the rate is, ranging from about 0.2 degrees per decade to around 1 degree per decade. You see here, especially over the Arctic regions, a very strong warming has been found in permafrost regions. Another important quantity is the active layer thickness. triangle. Each triangle on this map represent one site that people have been measuring active layer thickness over the years. This is how we do it. You go to one of the places end of this summer. So for instance, in Alaska, it's around late August. It was me a few years ago. One of the typical method to measure thickness active layers using mechanical probe is very straightforward. You just stick a metal probe as hard as you can. I was trying very hard. I was stick it to the thaw active layer until you reach this table where it's interface between permafrost and active layer, and then just pull the probe out and measure the thickness. People, dedicated permafrost scientists have been doing this for many, many years, and this is the results we have obtained. Again, showing the time series over, in this case, 30 years in different locations in Russian Europe, European Rus, in Northeast Siberia, and see here, actually, in most of the places, active layer has been increasing over time because permafrost beneath it thawing. One interesting location to note is the North Slope of Alaska, where the ground temperature has been rising, if you recall from my previous slides, but active layer thickness remain relatively stable. There's no trend over the 30 years time series. Last but not least is the subsidence. I'm showing this very nice figure from this latest review paper that just published last month, summarizing the ground subsidence rates as in the centimeter per year that will represent the size of the circle. Again, the larger the circle is, for instance, in northern Siberia, in this part of Canada, the ground subsidence rate was larger, higher than 3 centimeters per year. Where in other places, when the size circle are smaller, indicates smaller, slower subsidence rates. The color of the rings represent different methods that we use to measure the subsidence. Many of the methods are field-based, campaign style. Talking about, for instance, thaw tubes. It's a tube that typically measure thaw depth, but also use it as a reference frame. You can go there every year in the summer and measure the ground level. That's what the Canadian colleagues been measuring over this part of the Mackenzie River Delta, zooming this region, and for 20 years or so. Okay? And from those measurements, they report subsidence rates about 1 centimeter per year. People also just directly put GPS receiver on the ground. That's showing the yellow circles, because you can imagine this is something that is very tedious, but it's a campaign style. Not widely used though, only a few places, about 3 to 4 locations in Arctic regions been doing this. My Chinese colleagues has been doing leveling work over Tibetan Plateau, again on an annual base. I myself also conduct something like ground-based laser scanning and others. Some other method use, of course, I'm going to talk mostly about GNSS-IR today, and the INSAR and the photogrammetry, all being used. Okay, and lastly is the color within the circle representing the duration. Other than a few locations that we have more than 20 years of measurements, many other places only have a shorter than 10-year duration. Keep that in mind, because that's where I think GPS-IR can really help, because we now have many sites have longer than a decade of measurements over time. And just to recap what I just talked about, as permafrost been warming, we have different things that are happening. We have warmer and thinner permafrost become warmer and thinner. Active layer, on the other hand, become thicker and thicker. One consequence is that ground going down, ground subsidence, that more ground going down and causing, in this case, natural hazards and damage to infrastructure such as roads and buildings. Subsidence, most time, if you talk about centimeters level of subsidence, seems to be gradual, but they also can have strong impacts on our environment and even the carbon cycle. Permafrost collectively stores about twice as carbon as those in the atmosphere. In the paper published in 2020, the title of that paper is carbon thaw rates doubled when accounting for subsidence in the controlled warming experiments in Arctic region. So what they found is that if in the certain areas where if you measure thaw subsidence, which is under those few centimeters, and then it turns out that if you count the subsidence, the grounds that going down, which is of course is a result of thawing of permafrost, and permafrost thaws and the carbon that previously frozen in permafrost become unstable, and microbes and bacteria become active, and those organic carbon can decay and release CO2 back into the atmosphere. This concerns many climate scientists because that would add more and more carbon into the atmosphere, making a positive climate feedback that can further strengthen the global climate warming trends. Now, back to this variety methods, but you look at over these very large areas, only very few sites, very few places that were measured using different methods. Okay, but it turns out over Arctic region, there are at least 200 plus continuously operating GNSS sites. Show you a couple of them. These are all from Canada, from northern Canada. So I usually get this question is, can those GNSS stations, they should be able to help us to measure thaw subsidence, right? They should be very useful. So I'm just keep posing this question. I'm gonna examine this one particular site. This is in northern Alaska. The station ID is SG27. This is what it looks like. This one is part of the Earth Scope, the US Earth Scope Plate Boundary Observatory. From the name of the network, it's mostly for studying plate motion. So this monument is about 3.8 meters sitting above the ground, but below the ground is actually sitting 5 meters below the ground. Okay? Because the purpose of this a station like this is to measure the solid Earth movements. So the whole monument is fixed, is entered very deep in the permafrost. So it's fixed to the solid Earth. So conventionally, if you use measuring the 3D position of the receiver, this is what you would get. This is only showing the vertical components. And this is what I downloaded from Nevada Geodetic Laboratory, showing the time series starting from 2022 till now, how the receiver moves vertically. Okay, I would need to emphasize again that since this is fixed to the solid Earth with the solid Earth, what's showing here is how this whole thing is moving with the solid Earth. So what we are seeing here is due to solid Earth movements. To interpret this, we presume mostly the trend is related to plate motion, and the seasonal cycle is related to the surface loading from the atmosphere and from the water. But what we care about is actually how the ground surface moves up and down due to the change of frozen ground. So this is the point I want to make. The first point I want to make is that when you're concerned with you only measure the receiver position, you are not measuring the frozen ground changes. You are measuring the solid Earth. This is where GNSS-IR help. Right? In addition, because for positioning, we use direct signal, but audience know very well that we have signals that also reflected from ground that can interact or interfere with the direct signal. And this interferometric pattern would change as satellites move in different elevation angles. By measuring how this reflective interference would change with the elevation angle, we would retrieve a variable called reflector height, which is defined as distance, vertical distance from the receiver's face center to the ground reflector. And we typically call it H. Now, here is, since this whole blue monument is fixed within the solid earth. If there's anything change of the ground surface, then we're gonna see some change in the reflected height. For instance, if ground goes up, reflected height would decrease. If ground goes down, reflected height would increase. In other words, if you take the inverse or take the negative of the change of reflected height, that directly tells us something about the surface position change. And that's what we need when we're concerning frozen ground changes. This is what we need. One other note to make is this is Arctic. Of course, there's not snow cover. When the ground is covered by snow, then the reflected height changes would give us snow depth. Showing you an example what the reflected height records at this particular site look like over an entire calendar year. That's from in 2016, from January to the end of December. This is reflected height is in meters. The change during the snow cover period reflect the change of snow height. So in this case, we have snow accumulation and have a relative stable phase for snow to be there, and then there's a fast phase of snow melting. So we're talking about snow depth change on the order of 20, 30 centimeters. But look at this. This is a period when the ground was not covered by snow. And this is, if you study snow, you're confident like this. But for me, who worries about frozen ground, I found this is particularly interesting. So I zoom into this. This is showing you the snow-free period from June, and in this particular year, till early November. So each dot is a daily change representative vertical position change of the surface from GNSS-IR. This is the first time we are able to observe this continuous subsidence over the thawing season from June to, in this case, early September, and fast freeze back, fast uplift during the freezing season. Why this is exciting? Because not until we have GNSS-IR, this is not with such a detailed level, we were not able to observe this pattern, cyclic elevation pattern. The mechanism behind, though, is well understood. I'll quickly explain. Throughout the thawing season, from June to September, there's a gradual vertical migration of the thawing front. So start from the thawing, temperature arises. So at least the surface in the early June, this much of ground thaws, and the core ice that was in the active layer start to melt and ground gradually subsided a little bit as the thawing front progresses deeper and deeper over the thaw season, then the ground going down gradually. Why the freezing back is faster? Because during the cold fall season, we have sub-0 degree air temperature above, we also have cold permafrost beneath. So the freezing fronts are migrating from both up, down, and bottom up. So making the freezing process faster. And as water in the active layer freezes into ice, the surface goes up. Inspired by this new GNSS-IR records, we construct a single variable temperature index model. I'm skipping the detail. I'm just telling you that this thick black line behind it integrates the temperature from freeze and thawing season. And we construct the one single variable. And that one single variable model can beautifully explain this cyclic elevation, thanks to the observation we got from GNSS-IR. Now I'm moving from a particular season to 21 years. So I have to, so in this box, showing you one summer. if you zoom in, that's what it will look like. Okay, but on this particular time series, it looks like a vertical line because it's a shrinked. It shrinks this summer season to this vertical small area. So each summer looks like a subvertical line, but the magnitude from here to here actually represent the seasonal subsidence on this throughout summer. I'm going to show you this 21-year time series. We have daily interval in each summer. Then we have 21 years, start from 2024 and to the last season. And this is the first time we got for permafrost because there's no other observations can give us such a records. So using such records, we're able to gain a lot of insights about what's happening beneath the frozen ground. First, let's look at the seasonal cycle. If we measure the amplitude of the seasonal subsidence, in some years it's about 6 centimeters, in some years it's about 5 centimeters, in some years it's about 12 centimeters. Okay? Now, that means we see very strong year-to-year variability. It's not always the same. Now, what's behind that? Why certain years the ground went down further than the other years? Obvious reason is the summer temperature. So I'm going to show you on the bottom is a thaw index. It's a way to represent how warm a particular summer is. So the larger the value is means warmer summer, and the lower the value is means that particular summer was cooler. The dashed line just means 20-year mean. So let's look at how this is related, the ground subsidence related to the temperature. If you look at the first year, 2004 was one of the warmest year in the 21 years. Of course, you have a very warm summer, the ground thaws more, and then the ground subsidence is more than 8 centimeters. And we found that very commonly in the very warm years, I highlight here the 4 years that have very warm summer, then the ground subsidence was larger. The only exception is here in 2012, when summer was very warm, the ground subsidence was actually one of the lowest. So this already tells us there's some complexities behind the response of the ground to air temperature. What's also interesting is in the one summer after, let's show in the pink line here, this summer is after extreme summer. Previous one was extreme summer. Next summer was actually a cooler than usual summer. Supposedly, the ground should not subside too much, but we found out that there seems to be a memory in terms of subsidence. In the summer followed extreme warming. Next summer, the ground still subsided more than usual. And it's not just this particular pair. In other pairs, for instance, in this one, after extreme warm summer, the ground next year has still some memory to subside more. This has never been reported before. Again, thanks to GNSS-IR measurements, we started to see such a memory of the ground in response to extreme warm summer. Now, let's look at this time series. We found that there's actually very strong subdecadal to decadal variability. You cannot simply fit a linear line across the whole 20-year time series. To capture this variability more closely, we probably should divide it into subdecadal periods. For instance, from 2004 to around 2012, when there was a generally warming trend, the ground has a subsidence trend over these 8 years. But later on, the ground went up, okay, over another 6 to 8 years, corresponding roughly to a period when air temperature gradually cools down over the summer, and then followed by another phases of subsidence. Also, since we have this 21 years, I was trying to fit a sinusoidal wave to this and found that this seems to be a 18-year period. Of course, I should elaborate that since we only have 21 years, so it can be be misled by this simple fitting of sinusoidal. Because what if there's by extending this longer period, what if the periodicity is no longer there? But this gives us a new inspiration is, there's some natural oscillation in the atmosphere and the ocean system. Would this such kind of 18-year cycle be related to atmospheric oscillations, for instance, Arctic oscillations or North Atlantic oscillations? This is something that we'll like to explore a bit further and see whether there's some correlation between such records with large-scale atmospheric oscillations. So just from this one single site, we're able to gain so much quantitative insight. This is just to recap. On the seasonal level, so we found the amplitudes can range from 5 to 12 centimeters. And we understand it is caused by progressive thawing in the summer and then faster freezing in the fall season. And this cyclic behavior can be described by a very simple composite model that can be used in other large-scale climatic models if people wish to. On the subdecadal time scales, we see this year-to-year variability about 2 centimeters. If you just trace the end of the season from here to there, there's 2 centimeters going down and 2 centimeters going up. So the interpretation behind it need to motivate us to modify or examine this subsurface structure. So I start with this talk saying active layer is sitting on top of permafrost. But if you examine it further, there's actually a transition zone between the active layer and permafrost. Within this transition zone, due to capillary and other frozen ground processes, it tends to accumulate a large amount of ground ice, shown here. For instance, you can visually see some chunks of segregated ice. And this transition layer acts to explain how it works in connection to GNSS-IR is in the extreme warm year, for instance, active layer thaws, and this transition layer start to melt and causing the ground to subside more. And in the next year, for instance, when the temperature was relatively cold, but the transition zones already thaws out in the previous summer. So it can continue to melt and to thaw. So in other words, the transition layer acts as a thermal buffer that can delay the response of the frozen ground to the external atmospheric forcing, and that it acting on the time scales at subdecadal time scales. That actually what I think explains this what we see here in the subdecadal scale. Now we have 20-year records. Now if you look at this 20-year records, if there is any long-term trend, that's related to what's happening in the permafrost. Okay. So in flat plate areas, this long-term subsidence is relatively small. It's on the order of millimeter per year or up to 2 to 3 centimeters per year. Motivated by these records from GNSS-IR, we argue that you need a long-term records like this. For instance, if you only have 10-year records, you will fit a line like this and you report there will be a 5 centimeter per year subsidence. Then what about this? Because the ground went up. So we have to have a long records like what I shown here in order to have a good representation of what permafrost will change in the warming climates. And of course, in order to fit a line of this, you have to consider the seasonal and subdecadal variations. Now, that was just one site. Remember, over Arctic region, we have 200 plus sites. Okay, so that's showing you the GNSS that's in blue. My message here is that there's so many potential this community can contribute to permafrost studies. The spatial coverage of existing GNSS network really complements with the permafrost network. can help to fill in some spatial gaps, for instance, in northern Canada around Greenland. So together, we are contributing to an ongoing effort to further promote thaw subsidence as an essential climate variable product for permafrost. GNSS-IR measurements give us continuous daily measurements at least over summers. They help us to develop a parameterized model for cyclic elevation changes. Some observations, some sites have been running for 1 or 2 decades, and some are still ongoing. For instance, the one I'm talking about today. They start to reveal very strong subdecadal variabilities and long-term climatic records. I didn't have time to talk too much today. But GNSS-IR can give us other observations. Well, talk about snow depths. GNSS-IR can give us near surface soil moisture, 5 to 10 centimeters, and can also quantify freeze and thaw status. Those are very important for study collectively and comprehensively permafrost dynamics and frozen ground hydrology. Observations like this would also provide possible synergy with other methods, in particular remote sensing methods, such as INSAR and LiDAR. That's what I want to share today. I will end my talk now and happy to take any questions if there are any. Thank you very much.
Yeah, thanks a lot, Lin. I really appreciate for such a clear and insightful presentation today. So your explanations were really, I would say, engaging and easy to follow. So thanks a lot. So it's time to have some questions. I have some questions, but looking into the chat box, people perhaps can post their questions there. I can start with 2 questions about and GNSS-IR. It's exciting news that you put lots of effort to behind this, that GNSS-IR can be used for basically a climate permafrost variable. That's a great effort, and hope that is going to be successful. So my question it's about the effect of snow. So most of these sites are impacted by snow accumulation, and in case that someone, or if the interest is related to the uplift and the ground heave, so the snow accumulation can be a problem here. So is there any way to somehow correct this, either based on the model or based on the observation? I've seen that some people try to put a GNSS antenna on the ground before it's snowing, and then when the snow accumulated and the GNSS antenna buried below the snow, they can somehow compare what GNSS delivers with respect to the GNSS-IR. So is this doable? I don't know. At which state is that?
Okay. Thank you for your question. I will go back to that particular slides. I'll just talk about snow. Yes, while I'm putting up slides, for us to study permafrost elevation changes on snow cover is an issue because that would mask out the subtle changes on the ground. I'm showing you the slides. This is exactly why the reason is, well, this example is if the surface covered by snow, then what GNSS-IR measures reflected height changes largely caused by change of snow depth, which is on the order of centimeters or larger. In order to study elevation change of the grounds, so we have to only focus on the snow-free days.
Mm-hmm.
And of course, as you point out, in many places in Arctic, starting right after summer, you have snow cover. Then we don't have the opportunity to study the heave. Okay, this is one of the rare cases in this particular site. We only have a few years out of 20 years. We have 2 to 3 years that we have this snow-free time window in the fall season. In most other years, already have snow cover. Is there any way your question is there any way to estimate or remove or correct for the snow effects
Exactly.
from the observation perspective? No, not feasible. But from an engineering perspective, it seems to say that if there's a way to remount antenna or even clean up the snow, it may be possible. But the point of using this network is they've been there for many years and
Right. Yeah.
continue operating with minimum maintenance. That's probably don't need to, if there's a particular reason to study freeze the periods, then you pick up to pay special effort. But for most of the cases, probably just have to restrict it to snow-free period.
All right. Okay. Thanks a lot. So is there a dedicated a project that installed GNSS-IR sensor for permafrost monitoring? Because as you said, most of the existing sites are installed for example, solid earth application like tectonic, earthquake, volcano, or ice sheet monitoring. So is there any project going on there?
Not from my own group. I'm
Mm.
aware some research groups are building and establishing GNSS-IR sites for snow originally, and now they would consider for permafrost because the principle is the same. But there's no large-scale efforts for building such network for permafrost only.
All right. Okay. So there are two questions in the Q&A. Um, the first question is from Kemali Altuntas. It says that thanks for this great presentation. I would like to ask that did you only use reflector height to monitor permafrost changes? And could more sensitive result be obtained by analyzing the DSNR phases instead of relying on the DSNR frequency, that is the reflector height? And have you tried this type of approach before, or the current precision is enough for your research aim? So there are a couple of questions.
Okay. Thank you for a question. I do have one slide that can help me to answer this question. So actually we have, so what we pointed out is, let me show you this. We can only focus on this part. This is work done by a former student, Jiahua Zhang. So the question is, for those of you who know reflectometry, you use the change of frequency to estimate reflector height. That's what we mostly use. That's what we cover today. But you can also use the phase information, the SSNR phase information, to infer soil moisture, and that's what Jiahua did. This is a permafrost sites, right? And the blue line is the GNSS-IR retrieval of the surface soil moisture, and the black is in situ measurements. We're basically using Christine's methods. The only thing that's new is this is still summertime. Since over summertime, as I explained, the ground would go down. Then in retrieving soil moisture in phase information, you need also consider this elevation change of the ground. So by incorporating elevation change that you learn from the frequency, by incorporating that, you actually can improve the soil moisture retrieval in cold regions.
Yeah.
I hope that helps. And
Right. Yeah.
so we have a paper published in the Cryosphere document the detail. This is according one of my other points at the end is GNSS-IR is not only for elevation change. It estimates snow depth. It estimates soil moisture. Together, these are all useful for study frozen ground.
Okay. Right. Yeah. Yeah, thanks. And there is another questions in the Q&A box. It's asked about the daily position in time series that is related to the each epoch. And asking about diurnal variation in understanding the permafrost. How useful is it? That's the question is not a bit clear, but it's mostly
Oh,
uh,
I
yeah,
think I got this question.
right. Yep.
Because there's diurnal change of the
Mm,
temperature,
yep.
right? So temperature can be above zero in the day, and temperature
Mm,
can drop below zero in the nights. So this is talking about diurnal changes. So of course that would the grounds would in certain time of the year the ground would thaws in the day and freezes at night. But for us, as we point out correctly, that we only use the daily, which is actually in the sense of taking the daily average of what the ground
right.
position is. So we
So
didn't consider the diurnal change
yeah,
of the
it's
ground.
not sensitive. But one thing that perhaps I don't know whether you take a look or not, the sensitivity of the monument to the temperature.
Right.
That's from summer temperature to winter temperature can be on order of the couple of millimeter, although it's smaller comparing to the displacement you observe is in centimeter scale, right?
Right. So it's a
Yeah.
good question too, because
Mm,
there's a thermal expansion or
mm,
contraction of the monument itself, depends on the material. This is why many of the sites which was built for solid Earth observations, including this site, is using wood monuments, which supposedly to minimize the thermal effects. And let me see if I have the title slide. This is actually made of wood.
right,
But we didn't crack for this. And then in general, yes, we need to consider the stability of the monuments because the whole assumption is the monument is actually rigid and stable.
right,
Right? In some cases, actually, colleagues realize that they put the monuments too shallow, until too shallow, and this monument actually been sinking over time, and then this is not gonna be useful for us to characterize the frozen ground changes until you correct for the monument's instability issue.
okay.
And there's also related some monuments are sitting on buildings in cold regions, and how are they
Mm,
useful? Then I think we need to consider those monument stability issues.
yeah, thank you. Uh, Still, there are some time to post your question in Q&A box. And my last question to you, Lin, today is about, I just saw the NISAR the text in one of your slides. So with NISAR coming, they are focused on permafrost and for measuring the subsidence and uplift. So I was wondering whether these data are available. I mean, the process data, not the raw data, the deformation data, the height changes are available to the community through the database services and etc. that they can
Okay.
use to validate, for example, NISAR or other SAR approaches.
Right. Okay. So Michael, are you asking the availability of the GNSS-IR or availability of NISAR data?
And the availability of GNSS IR process data. I mean,
Oh, okay.
yeah.
So for us, okay, maybe also pull up that slides. Because if you know any of what I did, I spent another half of my career time at least thinking
Yeah.
about NISAR problems. Um, let's see, it's the same slides that I should show you. And I can mention NISAR, which is the upcoming US-India joint SAR mission, which can study permafrost deformation. So to direct answer McCann's question is for us who have produced GNSS-IR match time series for permafrost, at least for the published work, we have published all the time series data sets. One frustration is this is not widely recognized or used. I've been talking to nice people that you should use this GNSS IR time series
Right.
as a way to calibrate and validate your INSAR measurements because there's actually a lot of benefits using that. They are both
Sure.
L-band, NISA's L-band, and there's also gaps between different L-band missions. Mentioned this. So GNSS IR times like this can use as calibration, validation, can help to bring the gaps and the
Yeah.
temporal gaps in particular, can also serve as reference points. I hope the INSAR community are listening and can make use of such time series.
Yeah, definitely. Thanks. Yeah. All right. Okay. So I think we have covered all questions, and then yeah. So if there are no, we still have time for some question, but if there are not more question, we can we can close our webinar. So I would say thank you again, Lin, for your presentation today. So I really appreciate. So before we finish, so I'm gonna announce that our next webinar will be planned soon on a biosphere. So I'll send out more details through the mailing list soon, and also Lin presentation will be available very soon via YouTube channel. And if you're attending EGU, there is a dedicated Genesis IR poster session this year, and that's as a heads up. And then yeah, so I think we can uh, close the webinar. Thanks again. Thanks everyone for logging in and listening to Lynn's talk. I hope that you enjoyed. It was a great talk. And until next time, I wish you a good day. Yeah.
Thank you. Have a good weekend, everyone.
Yeah. Bye bye. Thank you.